Okay, so welcome to this next video in the playlist on the cardiovascular system. In this video, what we're going to do is continue our discussion of endothelium-dependent hyperpolarization by talking about nitric oxide, or NO, as the endothelium-dependent hyperpolarization factor. So we're going to see what evidence is there that nitric oxide is the endothelium-dependent hyperpolarization factor. Okay, so I'm going to just summarize what we've seen in previous videos, because you'll realize at the moment, if you have watched my previous videos, that the title to this is contradictory to what I've told you in the previous videos. So remember, in 1984, Bolton et al. Discovered endothelium-dependent hyperpolarization. They discovered that if you stimulate the endothelial cells of the blood vessel, so let's draw a little blood vessel. We'll simplify it down, so we'll just draw the most core layers of the blood vessel. So let's say this is the basement membrane on which the endothelial cells are sitting. So here are the endothelial cells, which actually line the lumen of the blood vessel. And then surrounding that, what you have is a layer of smooth muscle cells, known as the tunica media of the blood vessel. So here we go. Okay, and then surrounding that, you'll have a layer of connective tissue known as tunica adventitia. Okay, so let's just colour this in. So this pink layer here, this layer represents the layer of smooth muscle cells, known as the tunica media. So this is the tunica media. Okay, and these endothelial cells here, sitting on their basement membrane, is the tunica intima. I mean, there are a few more layers of, that are in the tunica intima. So there is a little thin layer of connective tissue underneath them, known as the subendothelial space. There's then another layer of connective tissue known as the internal elastic lamina. But to keep our picture nice and simple, we'll just have this as the tunica intima. And tunica, by the way, means a layer. Okay, so this literally means the close layer. Intima comes from the same word as intimate, so it means close. Okay, and then surrounding the tunica media, you then have a layer of connective tissue, which we'll call the tunica adventitia, the role of which is to connect the blood vessel to the surrounding structures of the body. So here is the final layer of the blood vessel, tunica adventitia. So here's a nice, simple picture of a blood vessel. Right, so we've seen that Bolton et al. In 1984 discovered that if you put acetylcholine onto the endothelial cells, okay, so if you stimulate the endothelial cells with acetylcholine, or indeed you can use another agonist for acetylcholine receptors, such as carbachol, CCH, okay, either of these agonists basically you can use, and if you stimulate these endothelial cells, what will happen is, if you record the electrical potential difference across a smooth muscle cell, so let's say we've got our smooth muscle cell here, so this is our smooth muscle cell in this tunica media, then if you record the electrical potential difference across the membrane of this smooth muscle cell, and let me just remind you what that really means so that I'm utterly confident we know what it means. So, basically, if you have a little man standing outside the cell in the extracellular fluid, he can measure electrical potential there. So I'll denote this electrical potential, big E for electrical potential, and then little e, subscript e, to denote extracellular. Okay, so he can measure the electrical potential extracellularly. He can then go inside the cell and measure the electrical potential intracellularly. Now, these two numbers are not the same, basically. So there is a difference between these two numbers. If you move from extracellular to intracellular, your electrical potential will change. And this is what's meant by the electrical potential difference, or the voltage from extracellular to intracellular. Now, people, when they're talking about the voltage across the cell membrane, they often drop the orientation. They don't write extracellular to intracellular. Strictly they should, because otherwise you don't actually know what they're talking about. You only know what they're talking about up to a sign. But when people say electrical potential difference across the membrane, they mean from extracellular to intracellular, so going in this direction. So basically what they mean is if you have a little man standing outside, he measures electrical potential extracellularly, and he then moves inside the smooth muscle cell and measures electrical potential intracellularly. How much does his reading on his little electrical potential measuring machine, how much does that change? Okay, so it's going to be equal to the new electrical potential, the electrical potential intracellularly, minus the electrical potential extracellularly, the old electrical potential. Okay, so that's what we mean by electrical potential difference across a cell membrane. Now, in smooth muscle cells, this is usually around negative 60 millivolts, okay? Now that means that the electrical potential of the intracellular compartment is lower than the electrical potential of the extracellular compartment, and it's lower by a whole 60 millivolts, basically. Okay, right. Now, what you find is that if you stimulate these endothelial cells with acetylcholine or carbachol, the electrical potential difference across this membrane gets hyperpolarized. And that means that the amount by which this electrical potential intracellularly is lower than the electrical potential extracellularly is going to get bigger. So maybe this number will become negative 70 millivolts, or maybe even beyond that. That phenomenon of this difference between them being amplified is known as hyperpolarization. Hyper meaning too much or an increase in something, and polarization meaning this polarity across the cell in electrical potential. Okay, right. So that is the phenomenon of endothelium-dependent hyperpolarization, because when Bolton et al. Removed the endothelial cells from the blood vessel that they were working in, which I think was a rat mesenteric artery, then it no longer showed this phenomenon. If you then poured the acetylcholine/carbachol through the blood vessel, it no longer produced hyperpolarization of these smooth muscle cells. In fact, it produced the exact opposite. It produced depolarization, because the acetylcholine and carbachol, when the endothelial cells weren't there to block them, they just went and acted on the smooth muscle cells directly. So this is known as the endothelium-dependent hyperpolarization. Endothelium-dependent hyperpolarization. Now, in previous videos, I've also told you about the experiments that followed in 1988 that were done by Chen et al. And Taylor et al. And basically, they showed that this endothelium-dependent hyperpolarization was not due to nitric oxide. And this is going to be contradictory to what I'm saying here in the title, and I'm going to show you how there are actually experiments which contradict what they did. So, what did Chen et al. And Taylor et al. Do in 1988? Okay, so in 1988, let's start with Chen et al. Basically, what Chen et al. Did was they inhibited nitric oxide. Okay, they exposed these endothelial cells to a lot of hemoglobin. Okay, so they took hemoglobin, HB, which I'll use HB to denote hemoglobin. Okay, and basically what they found, well, why should hemoglobin block nitric oxide firstly? Hemoglobin binds to nitric oxide. Okay, so let me just draw this briefly here. So Hemoglobin is a protein which consists of 4 proteins stuck together. The 4 globin proteins stuck together. So I'll draw it like so. Okay, so it's a tetramer of globin proteins. Okay, and you have 2 beta globin proteins and 2 alpha globin proteins. Okay, so this is each one of these is a globin protein. So this is specifically alpha globin, but you have 2 alpha globins positioned diagonally opposite one another, and then 2 beta globin proteins. Okay, Right, so you tetramize, well, you put these 4 proteins together to make the hemoglobin protein, and then you also add on what are known as prosthetic heme groups. So to every single one of these proteins in the hemoglobin protein, okay, so to all of these globin proteins, what you do is you add on what's known as a prosthetic heme group. Okay, so a prosthetic heme group is a molecular structure which has an iron, a ferrous iron cation at the centre of it. So let me discuss this structure in a bit more detail. Okay, so if I draw this square larger, basically what you have is you have a ring of atoms. You have a ring, basically, a chemical ring, which surrounds an iron cation, like so, which has 4 bonds, 2 of which are proper covalent bonds, and 2 of which are sort of just weak ion dipole bonds. Okay, right, so the point is, though, it's got 4 groups coordinated around it and forming some sort of interaction, some sort of bond with it, whether it be a covalent bond or an ion dipole bond here. Okay, so this ring surrounding the ferrous cation, so let me colour this in. So this ring surrounding the ferrous cation is a porphyrin ring, and I say it's a porphyrin ring rather than the porphyrin ring because a porphyrin ring is a very general chemical structure. Okay, and the porphyrin ring that you use in hemoglobin is a very specific example of a porphyrin ring. It's a specific molecule. You can draw every single atom out of this porphyrin ring, and that's the porphyrin ring you use in heme. Whereas porphyrin rings as a chemical family, they can vary hugely. So the porphyrin ring you use in heme groups is an example of a porphyrin ring. So the porphyrin ring family is far bigger. Okay, and then what you do is you stick this iron cation at the centre of the porphyrin ring, and that creates you this heme group. Now, basically, this iron cation here, which has a double positive charge, it's divalent cation, and that's why it's called a ferrous cation. So iron cations can take different forms, okay? Iron can become divalent cations, but it can also become trivalent cations, and the trivalent cations of iron are known instead as the ferric cation. And at the centre of heme groups you have the ferrous cation, not the ferric cation. Okay, so at the centre of this heme group you have this ferrous cation, and basically if we draw a picture of this, here's the ferrous cation, and then round the outside of this you have this porphyrin ring structured here. Okay, so let me colour this in turquoise. And basically the porphyrin ring is a very planar structure. It lies in a plane, and all these 4 coordinate bonds, as they're called, that are around the iron cation, these 2 covalent bonds and these 2 ion dipole bonds, they are within the plane. Now basically this iron cation can coordinate 2 more bonds. It can coordinate a bond from above, and it can also coordinate a bond from below. So what happens is that you can take these heme groups and you can stick them onto proteins, because molecules, functional groups in the proteins can interact with the iron cation. So for instance, they can take this 5th coordinate bond here. Okay, so indeed that's what we're going to do. We're going to take 4 heme groups and we're going to bind them to these globin proteins here, basically, 1 to each globin protein. And you'll notice that binding of the heme group to the globin protein is only going to use 1 of these spare coordinate bonds up. It's going to use the 5th one up. The 6th one will still be free, and that's usually where oxygen binds. So oxygen will usually come and bind in the 6th coordinate bond to the heme groups, which are now known as prosthetic heme groups. Prosthetic just means that they've been added on to something. So a prosthetic limb is an added on limb. So these are prosthetic heme groups because they've been stuck on the side of the proteins. They're not part of the proteins, they're a prosthetic group. Okay, so you put a prosthetic group on each of the globin proteins, and then in the 6th coordinate bond, this iron cation, this ferrous cation, will coordinate an oxygen molecule. Okay, but these ferrous cations in their 6th coordinate bond can also bind nitric oxide, and we'll continue our discussion in the next video.